Recently, my chemistry teacher brought up the idea of chemical equation balancing. So that's going to be the topic of today's video. Now, in a future video, we're going to be doing the same thing, but automating it using Python and its libraries. So stay tuned for that. But in this video, we're using algebra to balance chemical reactions. So what do I mean by balancing chemical reactions? Well, let's say we have ethane, C2H6, along with oxygen in our reactants. And for our products, let's say we have carbon dioxide, CO2, along with water, H2O. Well, you notice how we only have, well, not only. So you notice how we have 2 atoms of carbon on our reactant side, but we only have 1 atom of carbon in our product side. And we want to have the same number of carbon atoms on both our reactants and product sides. But we want this to be the case for all of our atoms. Why did I say all twice? All of our atoms. So, to fix this up, let's say we have 2 molecules of carbon dioxide. Well, now we have 2 atoms of carbon and 2 atoms of carbon. Excuse me. So we have the same number of atoms of carbon on both our reactants and product sides. So now let's do the same for our remaining atoms. So for hydrogen, we have 6 atoms of hydrogen on the reactant side, and we have 2 atoms of hydrogen on our product side. So we must have 3 molecules of water to have 6 atoms of hydrogen on both our reactants and product sides. Now for oxygen, well, you notice that we have 2 molecules of carbon dioxide, giving us 4 atoms of carbon, and we also have 3 atoms of oxygen. And when I said carbon there, I meant oxygen. My bad. So that gives us a total of 7 atoms of oxygen on our product side. And notice how we only have 2 atoms of oxygen on our reactant side right here. Well, we could have 7/2 molecules of oxygen, so we would have the same number of oxygen atoms on both our reactants and product sides. But we don't really want that 2 in the denominator right here. We don't want that 2 in the denominator right here. So we're going to have each of these molecules being multiplied by 2. We're going to be multiplying everything by 2. So we're going to have 2 molecules of ethane, C2H6, and now we're going to have 7 molecules of oxygen. And on our product side, we're going to have 4 molecules of carbon dioxide and 6 molecules of water. And there we go. We successfully balanced a simple chemical reaction. Now let's say we want something more complex. Well, earlier this year, I looked into this reaction called rocket candy. So rocket candy. And what it is that it acts as a propellant for model rockets, for rocket enthusiasts. So let's take a look at it. Well, it usually has an oxidizer of potassium nitrate, which is KNO3, and it uses sugar as its fuel. So for our case, let's say we're using sucrose and sorbitol for our sugar. So sucrose has a chemical formula of H22O11, and sorbitol is going to have a chemical formula of C6H14O6. So these are our reactants. Now for our products, which are going to be here, so our products, since this is also combustion, we're going to have both carbon dioxide and water again, so H2O and carbon dioxide, CO2. But you notice how we have nitrogen as one of our reactants right here. Let me change my color so the outline makes a little more sense. So we have nitrogen in our reactants right here, which must mean that we have nitrogen in our products. So we're going to have nitrogen, a molecule of nitrogen, and also we're going to have potassium carbonate. So potassium carbonate, I looked into this reaction a little bit more, and it turns out that potassium carbonate is usually a product from this chemical reaction. So potassium carbonate. So this is a salt, and it is soluble in water, but it has the formula of K2CO3. So K2CO3. And now we want to balance this chemical reaction. Well, we could use some similar steps as what we did earlier in our previous reaction. So first off, let's say that we have A molecules of potassium nitrate, B molecules of water, C molecules of carbon dioxide, D molecules of nitrogen, and E molecules of potassium carbonate. And I'm also going to have F molecules of sucrose and G molecules of sorbitol. Well, you notice we have 5 different atoms taking place. So we have K, N, O, C, and H, right? So that means I'm going to have 5 equations. And you might be asking, how do we get these 5 equations? Well, we could use the idea that there must be the same number of each atom on both our products and reactant sides. So for example, in our case for potassium, we're going to have 8 atoms of potassium on our reactant side, and we're going to have how many atoms of potassium in our products? We're going to have 2 atoms of potassium on our product side. So we could do this for our other 4 atoms, and this will give us a total of 5 equations. Now we want to have our 5 equations and 5 unknowns, but currently we have, well, we have 1, 2, 3, 4, 5, 6, 7. We have 7 unknowns and 5 equations. So that must mean that we have 2 of these coefficients for these molecules given to us already. So let's say we have, I don't know, well, if we don't have these 2 coefficients given to us, in our case, let's just say F and G, so F and G, if we don't have these given to us, then we can't solve for A, B, C, D, E, F, G. But now, if we have F and G given to us, the number of molecules of sucrose, let's just say that's just going to be 1, and the molecules of sorbitol, let's just say that's going to be 2. Well, now we have 1, 2, 3, 4, 5 unknowns and our 5 equations over here. Oh, I kind of drew that wrong. And we're going to have our 5 equations over here. So now we can get to writing down all of our equations. So we already written 1 equation, but let's write down the remainder of our equations. So for nitrogen, we're going to have A atoms of nitrogen in our reactant side, and we're going to have 2D atoms of nitrogen on our product side. Now for oxygen, we're going to have 3A atoms of oxygen, along with 11 atoms of oxygen and 12 atoms of oxygen, excuse me. And for our products, we're going to have B atoms of oxygen and anything else, 2C atoms of oxygen, along with that 3E atoms of oxygen. So that's going to be our equation for oxygen. And now we're going to go to carbon. Now we're going to do the same thing. So we're going to have 12 atoms of carbon over here. And where else is carbon present? We also have another 12 atoms of carbon over here. And now let's go to our product side. So for our products, we're going to have carbon present here. So we're going to have C atoms of carbon. And we're also going to have E atoms of carbon over here. Okay, so now finally to our last equation for hydrogen. So hydrogen, where's hydrogen present? We have 22 atoms of hydrogen here. Where else is hydrogen? There's also going to be 28 atoms of hydrogen here. Okay, so 28 on our reactant side. And on our product side, we're going to have hydrogen present here, 2 B atoms of hydrogen, and that is all. Let me redraw that K because that eraser tool kind of got rid of it, but oh well. So now we have our 5 equations, and our 5 unknowns are going to be A, B, C, D, and E. And we want to find out what A, B, C, D, and E are, so we know our coefficients for each of our molecules. And with that, we have balanced the chemical reaction. So what can we gather from our 5 equations so far to be able to find out what A, B, C, D, and E are? Well, we know that A is going to be equal to 2E, and A is also going to be equal to 2D. Well, and we also know that A is going to be equal to A. I know, mind-blowing. So that'll give us 2E is going to be equal to 2D. So that'll give us E is equal to D if we divide 2 to both sides. So now we also know E is going to be equal to D. Let me actually switch colors so that it's a little bit more separated from our equations, our given equations. So E is going to be equal to D. Okay, so now what can we gather from this? Well, not much at the moment, but what we can do is we can simplify it a bit. So here we can simplify it into 3A plus 23 is equal to B plus 2C plus 3E. There we go. And now for our next equation, what can we do? Well, 24 is just going to be equal to C plus E. And for our last equation, well, it's going to be 50 is going to be equal, oh, that looks like a 30, oh no. 50 is going to be equal to 2B, so that'll give us that B is equal to 25. So, boom, we already know what B is. We already know that we're going to have B molecules of water. Okay, so now what can we do from here? Well, you notice how E is going to be equal to D, how A is equal to 2D, and what else? Well, we know that A is going to be equal to 2D and E is going to be equal to D. And if you look at this equation right here, we notice that, well, we have many different unknowns popping up. We have A, B, C, D, and E, right? And we want to find out our unknowns, right? So what we can do is we can plug in a common variable for each of these unknowns. Let's say D, not variable, but another unknown for each of these variables. So for A, well, A is going to be equal to 2D. So that will give us 6D plus 23 is going to be equal to, well, B is going to be equal to 25 because it's right here. So B is going to be equal to 25. B plus 2C, well, you know that C is going to be equal to 24 minus E. If, I forgot the minus sign there. Let me erase that and draw that minus sign. Well, from this equation right here, this one right here, we notice how we can subtract E to both sides, which will give us 24 minus E is going to be equal to C. And now with that, we can plug that in for C. So C is going to be equal to, well, 2 times 24 minus E, because C is going to be equal to 24 minus E, but we're going to be multiplying that by 2 because, well, we have 2 of C. There we go. And now for E, well, we know that E is going to be equal to D, so I'll give us 3D, because E is equal to D, which is right here. Okay, so now from here, well, notice how we have all of our variables being the same, D, except this one right here. But like how I said earlier, E is going to be equal to D, so we can replace this E with a D, because they are equal. It's like 24 is equal to 24. They're the same. Okay, so now we can simplify this up a little bit. Let me actually redraw that over here. So C is going to be equal to 24 minus E. So let's simplify this equation over here. So 6D is going to be plus, and now we're going to subtract 25 to both sides, giving us minus 2. So 23 minus 25 is going to be minus 2, negative 2. And on our other side, we're going to have, well, 48 minus 2D by using the distributive property, plus 3D. And we're simplifying this even further. 60 minus 2 is going to be equal to 48 minus 2D plus, no, wait, I did not even simplify anything, plus D, because minus 2D plus 3D is going to give us D. And now from here, we can subtract D to both sides and add 2 to both sides, which will give us 5D is going to be equal to 50, giving us D is equal to 10. There we go. Let me put a line underneath this so that we know that that is one of our coefficients. So now we know B and D. Well, what else can we find out? Well, remember that E is going to be equal to D, right? So E is going to be equal to 10 too, because if D is equal to 10, E is going to be equal to 10. And we also know that A up here, over here, A is going to be equal to 2E and A is equal to 2D. So now we also know what A is. So A is going to be equal to, well, 2 times 10 is going to be 20. So now we know A, B, E, and D. And now how do we find C? We have this equation right here, which is 24 is equal to C plus E. And since E is going to be equal to 10, we can subtract 10 to both sides, giving us C is going to be equal to 14. And there we go. So let's rewrite our original chemical reaction out as in balanced form. So A is going to be equal to 20, there we go, potassium nitrate, and then we're also going to have our 1 molecule of sucrose, and we're going to have our 2 molecules of sorbitol. I'm drawing this really big, but oh well. And these are your reactants. And for our products, well, we're going to have B molecules of water. So B, where's B? B is going to be 25, so 25 molecules of water. And we're going to have C. C is going to be equal to 14, so 14 molecules of carbon dioxide, CO2. And D is going to be equal to 10, so that'll give us 10 molecules of nitrogen. And for E is going to be our molecules of potassium carbonate. So E is going to be equal to 10, so 10 K2 CO3. So this is our balanced chemical reaction of this right here. This one right here. And there we go. So we successfully balanced a more complex chemical reaction using algebra. Now, like I said earlier, there's going to be a future video discussing this very same topic, but we're going to be using Python and its libraries to automate the process, so we don't need to do all this work. It just automatically shoots back out a number, not a number, but our equation with our balanced equation right next to it. So there we go. So stay tuned for that one.